This is Lab 2. In this lab, we will be going over projectile motion. The purpose of this lab was to create a computer module that can predict real-life projectile motion. On top of our basic kinematics equation, we also added a new force called drag. Drag is equal to the magnitude of the velocity squared times the drag coefficient, which is b in the equation, times the unit vector of the velocity. The two models above show the graphs taken from the Tracker and GlowScript app, with the right graph being from Tracker and the left being from GlowScript. This slide included our source video and our model. The conditions from our source video are that the ball is not going to have any forces acting on it besides what we assume is gravity and air resistance. And the surroundings of our ball that we measured was just the air, so there was no contact with the hand or the table that we included in our measurements. This is a video of our ball. So when we flick the ball up, as soon as the ball leaves my hand, that's when we started taking our measurements, and then right before or right as the ball touches the table, that's when we stopped. And this is our code model running. As you can see, that you have an arrow pointing down, which is which represents gravity. You have the orange arrow, which represents the where the ball is going on the x-axis, and then the purple arrow represents where the ball is currently going. So the reason our ball is going the opposite way compared to the video is because due to the instructions, they wanted us to go along the positive x-axis, and so that's what we modeled. On this slide, we have our code. On line 74 of our code is the start of our function. T is equal to, or is less than, while t is less than 0.4, defines how long we want our code to run. So our ball was only in the air for about 0.4 seconds, so that's how long we set it to be. Vmag squared equals the magnitude times the ball's velocity squared. So that's where we get our the magnitude of our velocity squared for our drag force. And then we have v hat, which is the unit vector of our ball. And then drag is equal to the drag coefficient times this vmag squared times v hat. And then the force of gravity is the ball's mass times g. And an fnet is fgrav plus drag. The rest below is our what actually makes the ball go. And so we have the ball's velocity plus what the change of the velocity is due to the force times how long our time intervals last. And then we have our ball's position, which is the ball's position plus where the velocity times how long we had it go for. Some sources of error are how we pointed out the paper ball in our tracker app. So the ball kind of blended in with the white background in part of the video, and so it might not be the exact middle. We were also not really able to identify a noticeable drag coefficient due to our ball. I mean, it could be for any number of reasons, but we did not notice a drag coefficient big enough to measure. So for our what if and what does it mean question, imagine if the ball were initially thrown straight up with the same initial speed as your experiment. If the ball were to be thrown straight up, we would expect it to land after the ball in our experiment landed, due to the fact that the speed of our ball in our experiment is split between the x and y axis. and the only uh axis that determines when the ball will hit the ground is the y-axis. So if you were to throw it straight up, the ball would have all its speed in the y-axis, meaning it would be a higher number, which means it would take longer for it to hit the ground. Does the model predict terminal velocity? We did not see that it could predict terminal velocity due to the short time span that we had. Um, what experiment could be done to show terminal velocity? If we were to throw our ball maybe for a longer distance and had it fall for a longer period of time, then we could probably be able to determine our velocity.